Picture this. You're in a massive, super high-tech electronics factory. You see robotic arms flying around, placing these tiny, tiny components onto circuit boards with just incredible speed. It's like a perfectly choreographed dance of automation. But even in the most perfect dance, there's always a couple of awkward moves. And in this factory, it's the components that are just weirdly shaped. They're too big or too tall, or they just don't fit the standard machines. This is what's known as the odd form problem. And honestly, solving it took a real stroke of engineering genius. So let's meet these troublemakers, the odd form components. In a world that runs on standardization, these guys are the rebels. We're talking about things you've probably seen like capacitors, LEDs, transformers. They're absolutely essential parts, but they just don't fit the mold. For years, the only way to deal with them was with slow, expensive, and kind of error-prone manual labor. This created a huge, huge bottleneck in what was supposed to be a lightning-fast process. So why is this such a big deal? Well, get this. A single, well-designed machine can do the work of 10 people assembling these parts by hand. Yeah, 10. That's the mind-blowing potential we're talking about here. So solving this one little problem isn't just a tiny improvement. It's a full-on revolution for the factory floor. So today, we are going to pull back the curtain on the brilliant engineering that cracked this case. We'll start with the problem itself. Then I'll introduce you to the machine that really changed the game. We're going to dissect its core mechanism, walk through its 5 key steps, and then we'll see how it all impacts the modern smart factory. Okay, let's really dig into why this is such a headache for manufacturers. It's not just about a quick pause in the action. When a multi-million-dollar production line grinds to a halt for just one person to insert one part by hand, the ripple effect is just enormous. It messes with everything down the line, your deadlines, your costs, and the overall quality of the thing you're building. Right, the most obvious problem is that everything slows down, but the hidden costs, that's where the real pain is. You've got higher labor bills for one, and you have a much, much higher risk of simple human error. Putting a component in backward, which can fry an entire board, or even just accidentally damaging a delicate part. It all adds up to inconsistent quality and one heck of a bottleneck. So you have to be thinking, there's got to be a better way, right? What if you could just teach a machine to handle these rebellious parts? Well, that's where our hero comes in. We're going to look at a specific piece of tech that was designed to solve this exact problem for a whole class of components called radial parts, things like capacitors and LEDs. And this is it, the radial tape feeder. This thing is a marvel of efficiency. Its whole job is to take these components, which usually come on a long strip of tape, and perfectly cut, shape, and position their little metal legs, we call them pins, so that a standard robotic arm on the assembly line can just grab them and place them like any other part. It's basically the perfect bridge between two different worlds of manufacturing. So let's pop the hood, right? Because at the very heart of this machine is a really, really clever piece of mechanical engineering. It's a system that's so well designed, it can do multiple complex things all at the exact same time, with perfect precision every single time. It's called the CCL linkage mechanism. Now, CCL stands for pin cutting, foot body positioning. I know it's a mouthful, but the idea behind it is actually pretty simple. It's just an integrated system that combines a bunch of crucial steps into one smooth, fluid motion. This right here, this is the secret sauce. And hey, don't just take my word for it. The source material itself calls it a unique CCL core linkage mechanism. And that word, unique, is super important. This isn't some off-the-shelf design. It's an innovative, often patented design that really sets this technology apart and solves that core challenge of handling these parts with both speed and care. Okay, so how does it actually work? I think to really understand the brilliance of this CCL mechanism, we're going to follow one single component on its journey through the feeder. We'll break the whole thing down into 5 super precise steps. So here's the game plan. It all starts with feeding the component in. Then comes a really critical clamp down. After that, we get the magic, the simultaneous action. Then the final positioning and release. And lastly, a surprisingly simple final adjustment. Ready? Let's trace the path. First things first, feeding. It all starts with a high-precision stepper motor that pulls the component tape forward in exact tiny increments. And this isn't just any motor. Its accuracy is what guarantees everything is perfectly positioned from the get-go. At the same time, a big guide wheel grips the tape so it travels smoothly, with no jams. See? Precision starts right here at step 1. Next up is what I think is one of the most important and clever steps, the clamp down. Before any cutting or shaping happens, a small cylinder pushes a little piece into place to firmly lock down the component's pins. Seriously, think of it like a surgeon's clamp, holding everything perfectly still before making a super delicate cut. And this quote explains exactly why that clamp is so critical. It stops the component from, quote, jumping when the cutting knife comes down. It also keeps the pins from getting bent or deformed. Without that simple clamp, the cut could ruin the component and bring the whole line to a halt. It's all about creating total stability before the main event. And now for that main event, the magic of the CCL linkage. A single-cylinder linkage from a top-notch maker like SMC or Kokanai performs 3 actions in one single, incredibly efficient motion. It cuts the pins to the perfect length, it positions the body of the component, and, if the job calls for it, it can even form the pins into a specific shape. One fluid movement, 3 critical jobs done, just like that. The very instant that cut is finished, a special positioning block makes sure the component's body is in the exact right spot. Then, the cylinder immediately pulls back, releasing the pins. And there it is. The component is now perfectly prepared, just sitting there, ready and waiting for the robotic arm to swing by and pick it up. So clean. But wait, what if the next batch of circuit boards needs a component with a different pin length? This is where the engineering gets really, really elegant. The entire CCL mechanism uses what's called an integrated floating design. This is just incredible. On older, clunkier machines, changing the pin length might mean a whole complex recalibration process. But here, you just loosen a single screw on this little green block and you change its height. That is it. It is so simple, it's so fast, and it means you have almost zero downtime when you're switching between different jobs. Okay, we've gone deep into the mechanics, right? Cylinders, pins, clamps. Let's zoom back out for a second and look at the big picture. Why does this one machine matter so much in a modern factory? Well, it really just comes down to this: speed, reliability, and cost savings. By automating this one tricky step, factories can run faster, they can produce way more consistent and higher quality products, and they can move their skilled human workers to do more valuable things. It's just a massive leap forward in efficiency. So, if you're going to take anything away from this, let it be these key points. This technology finally automates those awkward odd-form components. Its secret weapon is that CCL mechanism doing multiple things at once. That pin clamp is absolutely essential for preventing damage, and the one-score adjustment makes it unbelievably flexible. All of this together, well, it's a key piece of the puzzle for building a true Industry 4.0 smart factory. You know, the radial tape feeder and its CCL mechanism are just such a beautiful solution to this really complex puzzle of movement and force and time, all happening in a tiny fraction of a second. It really makes you wonder, doesn't it? What other everyday objects that we use, that we see all the time, are hiding this same level of invisible, absolutely ingenious engineering?